CCI Crash Course Instrumentation presents Episode number 67, Current Dividers in Real Life, Which Path Gets More? Cold Open. When a road splits, more cars take the wide, clear lane. In circuits, when a node splits into branches, more current takes the easier path. Today we make current dividers feel obvious. No formulas, just words, arrows and meters. Viewer promise. By the end, you will predict which branch takes more current, prove it on the bench, and sanity check any parallel split using KCL language. Incoming equals outgoing. Quick bridge from episode 66. At a node, the ins equal the outs. We called each branch incoming or outgoing and checked it with a clamp or DMM. Now we ask, when paths run in parallel, which one carries more? Section 1. Intuition. Path ease. Think of two lanes, one smooth and wide, one rough and narrow. Traffic prefers the easy lane. In circuits, ease means lower opposition to current. We will call that lower resistance without writing symbols. Plain rule of thumb, the easier, lower resistance branch takes more current. The harder, higher resistance branch takes less. Section 2. How to read a divider at a glance. Step 1. Find the shared node where the source feeds multiple branches. Step 2. Mark quick arrows away from the node on each branch. Say outgoing for each. Step 3. Compare the parts in each branch. Thicker conductor, shorter run, or a smaller resistive load usually means an easier path. Step 4. Rank the branches from easiest to hardest. Expect the ranking of currents to match this list. Section 3. Bench Minilab. 2 and 3 branch splits. Build a safe parallel board. Supply, node, 2 resistors in parallel, return. Then add a third branch for a second run. Close the switch. Use a clamp meter, or insert the DMM in series 1 branch at a time to read each branch current. Say it out loud. Branch A outgoing, branch B outgoing. Totals at the node equal the incoming feed. Observation: the branch with the smaller resistive value carries more current. When you add a new branch, the incoming current rises and each branch's share adjusts, but incoming equals outgoing still holds. Pro tip: if a reading shows a negative sign, your arrow guess is flipped. Keep your words consistent and carry on. Section 4. Common misreads and fixes. Misread: assuming equal split. Fix: compare branch E's first. Only identical branches share evenly. Misread: forgetting hidden returns, like a chassis bond. Fix: trace every conductor touching the node. Misread: clamping both go and return in the same jaw. Fix: clamp a single conductor so the meter doesn't cancel the fields. Misread: calling direction by insulation color. Fix: trust the schematic and the node, then verify with the meter. Section 5. Real-world snapshots. Residential panel. 2 lighting circuits and a space heater tied to one feed split the current. The heater's branch takes more during heat-on. Industrial MCC bucket. A feeder splits to a motor drive and to control lighting. Expect the drive branch to dominate while lights take a small share. Test bench. 2 parallel shunt paths on a prototype. The lower ohm shunt steals the lion's share of current and cools less if sized correctly. Section 6. Field checklist you can use today. Pick the split node you care about. Draw arrows away from the node and say, outgoing. Rank branch E's, shorter, thicker, fewer devices, smaller resistance, more current. Measure 1 branch at a time with clamp or series DMM. Confirm incoming equals outgoing at the node. Tiny historical note. Telegraph trunk lines used parallel repeater paths to share load. Techs quickly learned that the path with more copper took more current. The language was simple. The easier wire carries the work. Tease for the next episode. Next up, KCL in the field, neutral balance, meter mysteries, and a quick diagnostic story where a hidden branch stole current. Call to action. If this made current splits click for you, Please like and subscribe so more students and techs can find it. Credits, on screen and spoken. Thank you to Tony Kupult and the open source community for the model materials that make Crash Course Instrumentation possible.